So we'll do another example. Let's take this alkyl halide. So I've got my aromatic ring. I have an alkyl halide. We're going to put in a Lewis acid catalyst. Any Lewis acid will work. I'll do iron bromide. If you notice what I've been doing, it's not a requirement, but most people just think it looks better. If you got a bromine here, we usually use like iron bromide or aluminum bromide. That's not a requirement. You can still use aluminum chloride or BF3 or any Lewis acid. Any Lewis acid will work. But most people just think it looks better to make them match. But it's not, that's not a requirement. They don't have to match. It would work with any Lewis acid. But most people just think it's prettier, I guess, to make them match. Okay, so I've got my alkyl halide, Lewis acid, and we're going to put an alkyl group onto the ring. Just like we did there before. There's my alkyl group. Does that look right? Okay. We don't get that. Why not? Let's go through our mechanism and see. Something didn't work right here for this reaction. In the previous one, we just stuck that alkyl group right onto the ring. So let's see what happens. Okay, mechanism is the same to start with. Alkyl halide. We're going to give electrons to the Lewis acid. So that part of the mechanism is the same. That bromine now has a full plus charge. That bromine's not happy. Being an electronegative atom, it wants a negative charge. Doesn't want a plus charge. It's divalent. Doesn't want to be divalent. Wants to be monovalent. Wants one bond. So that's going to break apart. Give us the carbocation. Be left with this anion. And in the previous example, we added that carbocation was our electrophile and added to the aromatic ring. But I just said that's not our product. What's the problem here? Watch for cation. Anytime you have a carbocation in a mechanism, watch for cation rearrangement. That is a primary carbocation. If you can get to a secondary or tertiary, it will want to do that because those are more stable. If you recall from Organic 1, primary carbocations can rearrange to a secondary. Secondary can rearrange, well, let me do one more. Primary can also rearrange to a tertiary. Secondary can rearrange to a tertiary. To do cation rearrangement, you must go to something more stable. Secondary to a secondary would never happen because I didn't gain anything. You have to gain something. You have to get to something more stable. Anything's more stable than the primary, so primaries will rearrange very quickly. If you recall our rearrangements, there's two rearrangements we can do. We can do a methyl shift or a hydride shift. Those shifts must occur from the beta position. Alpha is where the cation is. The next one out is beta. So we need to shift something from the beta position. That beta carbon has got hydrogens on it and it has a methyl group, so which one do I do? Well, you always do hydride first because it's a smaller group, easier to move. You only do methyl if you don't have any other option. If there was all methyls, then I would have to do a methyl shift. But we're going to do hydride first. It's a smaller group, easier to move. I'm moving a hydride over an H minus. From the beta position, we're going to move a hydride over H minus. And so that will give us our hydride shift here. That now gives us a secondary carbocation. That is more stable than the primary. So that rearrangement will occur very quickly because we're going to something more stable. Now there's no way I can get it to a tertiary. I don't even have enough carbons. Secondary is as stable as we can get. And that's what reacts with the aromatic ring. Now, everything's the same now. So that's our aromatic ring is going to give a pair of electrons to the electrophile. Now we need to get our catalyst back and we need to get the hydrogen off of the carbon where we just put our electrophile so that we can get that aromatic ring back. Right now we don't have the catalyst. We've got this anion back here. Let me redraw that. So we're going to take a bromine off to come and grab that hydrogen, and the electrons kick toward the plus charge to form the double bond again. So we get our aromatic ring back. There is our organic product. We also make HBr as a byproduct and you get the catalyst back. So this one underwent cation rearrangement. So that's one of the bad things about the Friedel-Crafts alkylation reaction is that we must watch for cation rearrangement with these because there is a carbocation involved. So watch for rearrangement. So that first product I drew there a moment ago, we don't get any of that. Or at least very little. Maybe you get 1 or 2%. This is going to be the major product where it rearranged. Questions on that? Now, normally, most people use the alkyl halides for the Friedel-Crafts reaction. We can also use alcohols. Alcohols will also work for the Friedel-Crafts alkylation. So let's look at an example of that. Let's take our benzene ring. I'm going to choose this alcohol as my alcohol. Any alcohol would work. And we still need a Lewis acid catalyst. Now, for some reason, don't know why, but for alcohols, the BF3 works the best as the Lewis acid catalyst. The others can work, but for some reason BF3 just works really well with the alcohols. I don't know why. So most of the time you're going to see BF3 as the catalyst when you're doing an alcohol. These don't work quite as well as the alkyl halides, and so they're going to need some heat. We typically heat these 50, 60 degrees, something like that. I'll just put heat. Doesn't matter about the temperature, but we do need heat. And we will put the alkyl group on to the aromatic ring. As a byproduct, we would get water here. But we put the alkyl group on. Now let's look at the mechanism. Mechanism is the same as what we did with the alkyl halides. I'll do the mechanism up through till we get to the electrophile, and then I'll let you finish out because it's the same as what we were doing there before. So, first step, we got the Lewis acid. That boron has got a large partial positive charge on the boron. There's only 6 electrons around the boron, and the 6 that it's got, the fluorines are pulling them away. So it's a big partial positive charge on the boron. It wants some electrons. Well, they can get it from the OH group, or alcohol. That alcohol will give a pair to the boron. That leaves a plus charge on the oxygen. And that puts a negative charge on the boron. Now that oxygen with a full plus charge is a good leaving group. That's going to leave off. That gives us our carbocation. That is our electrophile. That is a secondary carbocation. There's nothing we can do to get it any more stable than the secondary. There's no way we can get to a tertiary. So it's stuck there. It's not going to rearrange. And we have that anion there. That we'll use later as a base. I said I wasn't going to finish it, but I'll go ahead and finish it. Let's take our carbocation. Take a pair out of the aromatic ring and give to the cation. There's our rhenium ion. We need to get our catalyst back. We also need to get our aromatic ring back. So we're going to take the OH off to come and grab the hydrogen. Electrons kick toward the plus charge. And that gives you the product and the water there as a byproduct. And we get our catalyst back. So we can also do alcohols. Alcohols will also work. Basically, anything that can form a carbocation will work for a Friedel-Crafts reaction. So let me give you another example of something else. We can do an alkene. Now for the alkene, we're going to use HF. We're going to use HF because we need a proton, an acid to protonate. We need an acid to protonate the double bond. And then the fluorine anion is a poor nucleophile. So we need a poor nucleophile. I don't want the halogen to add to the cation. We want the cation to react with the aromatic ring. So fluorine is a very poor nucleophile. So this protonates the double bond, and that gives us the carbocation. That's our electrophile. And then that will add to the aromatic ring. I'm not going to go through the rest of the mechanism. We'll just put up the product. But you can get that alkyl group onto the aromatic ring. So you can use an alkene because we can make a carbocation out of that. So like I said, basically anything that gives a carbocation we can use in a Friedel-Crafts reaction. Any questions on that? Yes?
What about a carboxylic acid? Can you use that?
No. Carboxylic acid, there's no way to get to a carbocation with a carboxylic acid. I could use, well, that's not a strong enough acid to do the protonating, so I can't use the acid there, and I can't use it as this part to put that onto the ring, because there's no way to get to a cation. So no, can't do a carboxylic acid. Other questions? Okay, let's go ahead and take our break just a little bit early, because this is a good place to got a little bit different topic here next. Now, we just saw with the Friedel-Crafts alkylation that we had to watch for cation rearrangement. So I had up there a moment ago that one product that we didn't make. I had a big X through that one. We didn't make that one because it rearranged when we tried to make it. What if I really wanted to make it though? What if I needed that compound for some specific purpose? How can I make it? How can I avoid the cation rearrangement? And that's what we're going to be looking at next. One of the ways that we can avoid that rearrangement. We're going to look next at a Friedel-Crafts acylation. And I'll come back to that compound a little bit later. We'll learn how to make that using a Friedel-Crafts acylation. So this is acylation instead of alkylation. We're going to be putting an acyl group on. An acyl group is a carbonyl with an alkyl coming off of one side. This is an acyl group. We've talked about that before. It's got an abbreviation of AC. Sometimes we'll abbreviate it AC. That's an acyl group. So we're going to be looking at putting an acyl group onto an aromatic ring. To do that, we're going to take our aromatic ring and react with, I'm going to stay generic here, and then I'll do some specific examples. We're going to react with an acyl chloride. We're still going to need the Lewis acid catalyst. And any Lewis acid catalyst would work. And we will put an acyl group onto that ring. As a byproduct, we get HCl here as a byproduct. But we have put an acyl group onto the ring. Now let's look at the mechanism. The mechanism is the same as what we've been doing. I'll stay generic here for the mechanism as well, and then I'll put up a specific example. Let's write a Lewis acid catalyst here. I'll use aluminum chloride as my Lewis acid catalyst. So we have the acyl chloride and my Lewis acid catalyst. It's the same mechanism. We're going to give electrons from the chlorine on the acyl chloride. Those are going to be given to the aluminum. That will put a plus charge now on that chlorine. And a chlorine with a plus charge is not happy. And so this will want to break apart. We could break the chlorine aluminum bond. We go right back to where we started. Or we can break the carbon chlorine bond. So you're going to take the electrons onto the chlorine. That gives us an acyl cation. And we also have the anion down here, the aluminum anion that we will need later to get the proton. But we've made an acyl cation. That acyl cation is our electrophile. Now, acyl cations are special. Acyl cations will not rearrange. Why will an acyl cation not rearrange? Resonance. It's stable because of resonance. We've got, let me just show you here. I'll redraw it and show you the resonance. We can draw resonance with the lone pairs on the option. You can bring those electrons in and you can draw resonance. May now be a triple bond. But we're going back and forth between those two resonance structures. So that's a pretty stable carbocation because of the resonance. So that's why they will not rearrange. They are stable because of resonance. So acyl cations will never rearrange because they have the resonance. Now, that acyl cation is what is our electrophile, so that's what adds to the aromatic ring. So now the mechanism is the same. Same mechanism from here on out is what we've been doing. We'll take the electrons out of the double bond of the aromatic ring and add it to the electrophile. So one carbon gets the electrophile, one gets the plus charge. I need to get the hydrogen off of the carbon where I just put the electrophile. I also need my catalyst back. So we're going to take a chlorine off of this anion. Come and grab the hydrogen, and the electrons kick toward the plus charge and reform our aromatic ring. And we put the acyl group on. There is our product. As a byproduct, we've just made HCl. Chlorine grabbed the hydrogen. I don't care about that. And we got our Lewis acid catalyst back. But here is our organic product. We have put an acyl group on to the aromatic ring. So let's look at a specific example. I'm not going to go through the mechanism again, but I'll put up a specific example rather than this generic. Taking benzene and I'll use this acyl chloride. Any acyl chloride will work. And we need a Lewis acid catalyst. Any Lewis acid catalyst will work. I'll use aluminum chloride. And so again, that's going to pull the chlorine off, give you the acyl cation. The acyl cation is what adds to the aromatic ring. there's our product. Let's do one more. I'll give you a hard one. Let's take this acyl chloride, and all I got to do on this one is put in a Lewis acid catalyst. The Lewis acid is going to pull the chlorine off, give us the carbocation. That's my electrophile, and it actually has an aromatic ring back here on the other side, so it reacts with itself. There's our product. So that one reacted with itself. That's as hard as you can get right there. That's a kind of a difficult one where it closes up on itself. So again, the catalyst pulls the chlorine off, gives us a carbocation right there on the carbonyl carbon. And we still take electrons out of the aromatic ring and add to the cation. So you can count your carbons, 1, 2, 3, 4, 5. It's going to be a 5 carbon ring there. There's my 5 carbon ring. So that one is hard as they can get right there. Questions? Let's look at another one. Now, you can also use, instead of acyl chlorides, we can also use anhydrides. An anhydride is an oxygen sandwiched in between 2 carbonyls. This is an anhydride. That's the generic formula for an anhydride. So anhydrides will also work for these Friedel-Crafts acylations. So let's look at an example of that. We'll use this anhydride. Still need my Lewis acid catalyst. And we will put the acyl group onto the ring. Now with this one as a byproduct, we get a carboxylic acid as a byproduct. But we care about that aromatic product. That's what we're trying to make. The carboxylic acid byproduct, we can wash that away with some base. Go in and do a base wash and get rid of that. Let's look at the mechanism here for the anhydride. First step of the mechanism, same as what we've been doing. We're going to give some electrons to that Lewis acid catalyst. There is a big partial positive charge on the aluminum. You're going to use the oxygen of the anhydride, the one right in the middle, and we're going to give a pair to the aluminum. That puts a plus charge on that oxygen. Any oxygen with a plus charge is a good leaving group. So we're going to break one of the bonds here on either side. It doesn't matter which side you use. We're going to break the bond on one of the sides between the carbon and the oxygen. I'll just do this one. We'll take it up onto the oxygen. That gives me my acyl cation. That is my electrophile. This piece that we will need later to get the hydrogen off. So my acyl cation there is what's going to react with the benzene ring. pair of electrons out of the double bond, give to that acyl cation. Now I need to pull the hydrogen off of the carbon where I just put the electrophile. Also need my Lewis acid back. So we're going to take this oxygen here off of the aluminum, and that's going to come and grab the hydrogen. And electrons kick in to get my aromatic ring back. So that gives us our product. And we also get the carboxylic acid as a byproduct. That oxygen grabbed the hydrogen and made carboxylic acid. You get that as a byproduct. And you get your Lewis acid back as well. Okay, so we can also do anhydrides. We can use acyl chlorides or anhydrides to do the Friedel-Crafts acylation. Questions?
Dr. Sully, I have a question. Are all of the anhydrides we're going to be given going to be symmetrical, where it doesn't matter which side?
Yeah, you'd want to use a symmetrical one. Otherwise, you're going to get a mixture of products. If you had one that was that was asymmetrical, you'd have a mixture. We don't want to do that. So we're always going to choose one that's symmetrical. Now, I mentioned, let's go back to that one compound a moment ago. So let's see how we're going to make. We know now how to avoid cation rearrangement. But how do I make this product that I had up there earlier? How do we make this using a Friedel-Crafts acylation? Because acylation is the only one we got that will avoid the rearrangement here. So we're going to first put on an acyl group. And we know how to do that. So we're going to do the Friedel-Crafts acylation. I need 3 carbons because this has got 3 carbons in the chain. So I'm going to use 3 carbons here, an acyl chloride that's got 3 carbons total. We need the Lewis acid catalyst. And I will put the acyl group on. So I've got my acyl group on. Oh, I forgot to write the section down. This is 15.7 A. We'll do A first here. And then we need to get to the product, we need to do what kind of reaction? What kind of reaction would this be? I'll give you the reagents in a moment, but just first, tell me what kind of reaction that is. Taking that carbonyl to a CH2. That's a reduction. So we need to do some kind of reduction here. Now we're going to look at 2 sets of reagents that can be used. There's many reagents that can be used here to do the reduction, but I'm going to give you 2. I think 2 is enough. The first one that we're going to do is called a Clemmensen reduction. This Clemmensen reduction only works for aldehydes and ketones. We know aldehydes and ketones are our most reactive carbonyl compounds. So esters won't work here. Carboxylic acids won't work. Amides won't work. So nothing else works. Aldehydes and ketones only. Those are our two most reactive carbonyl compounds. So the Clemmensen reduction uses a zinc mercury alloy, and it's done under acidic conditions. We use hydrochloric acid as the acid. It's always hydrochloric, and we heat these up to reflux. And that will reduce that carbonyl to a CH2 group. Now the mechanism is not known for how this works, we just know it works. So here I have a ketone and we are reducing it to a CH2. Now we've done reductions in the past. We've done hydrogenation, we've done lithium aluminum hydride, sodium borohydride. So any of those others that we've talked about, sodium borohydride or lithium aluminum hydride or the hydrogenation, any of those three would have made the alcohol. But the Clemmensen reduces it all the way to an alkyl group. So it reduces it further than the others do. So it's a different reduction. But both are reductions, you just get different products. Now, I mentioned that I'm going to, well, let's do one more here. I'll give you one more example. So I have a ketone here. You can also do aldehydes. So let me just put an aldehyde up here. Aldehyde will also work. That aldehyde would become a CH3 in this case. You're reducing the carbonyl to a CH2, but since it's an aldehyde, we already had one hydrogen. So if that carbonyl carbon gets reduced to CH2, you already got the one more hydrogen. That makes CH3. So I'll just put the CH3 out there. You can see it got reduced. Now I mentioned I'm going to give you two reagents. So we have the Clemmensen reduction. That's one set of reagents. Clemmensen uses zinc mercury alloy and hydrochloric acid. The other one is called a Wolff-Kishner reduction. It also only works for aldehydes and ketones. So I'm going to go back to that same ketone that I had there a moment ago. And let's look at the Wolff-Kishner reagents. Wolff-Kishner uses hydrazine, this is hydrazine, and we use a hydroxide base. Normally it's potassium hydroxide, just because it's soluble in the hydrazine. Sodium hydroxide is not very soluble in the hydrazine, so it's always potassium hydroxide. So we use hydrazine and potassium hydroxide. That will reduce that carbonyl down to a CH2, just like we did with the Clemmensen. We get the same product here. So again, that works for aldehydes and ketones. We can do any aldehyde or ketone. Now, those of you that are in the lab, don't confuse this one with the luminol lab that we did. Luminol used hydrazine, but we didn't have the base in there in that step. You got to have hydrazine and the base to do the reduction. So in that luminol we used hydrazine, but we didn't have the base till much later. So that was not a Wolff-Kishner reduction. That's a totally different reaction that we did in lab with the luminol. Okay, so any aldehyde or ketone will work. Let's look at another example. Okay, if you look at this one, examine what we have. We've got a ketone here, and we have an ester. Well, esters don't work, but the ketone will. So the ketone gets reduced, but the ester stays the same. And there's our product. So we don't touch anything except aldehydes and ketones. That's the only thing that the Wolff-Kishner or the Clemmensen will work with. So that carbonyl gets reduced down to a CH2 group. Questions?
Is this in one step? Like, I know we don't know the mechanism, but like when we like, you say what's the reagent? Like, are we just putting like?
Yeah, it's one step. These have to be added together. Yeah, that has to be added together. Same thing with the Clemmensen. You're using the zinc mercury alloy and hydrochloric acid together. You know, there is no steps there. You just put it all in together. Other questions? Okay, we are next going to be looking at, we've been putting these groups, all these groups onto an aromatic ring. So we've been doing electrophilic aromatic substitution. And these groups that are on an aromatic ring, a substituent that's already on there. So all of my examples that we've done up till now, I've taken a plain benzene and reacted with an electrophile. But what if the aromatic ring already had something on there? Already had a substituent. Where is the next substituent going to go? That's what we're going to be looking at next. It's going to matter where you put it. If we start with plain benzene, there's nothing on there. It's just hydrogens. So it didn't matter where we put it. It's the same thing. But we're going to be looking at a substituent already on there, and that the substituent that's already on there is going to direct the next one as to where to go. And that's what we're going to be looking at next. So let's first look at two different types of groups. We have a substituent that's already on the aromatic ring, can either be an activating group or a deactivating group. Now let's define that. An activating group is a substituent that makes the aromatic ring more reactive than a plain benzene. A deactivating group would be just the opposite. A deactivating group is a substituent that makes the aromatic ring less reactive than a plain benzene. Okay, so we have two different types of groups. We have activating groups and deactivating groups. Now, I'm going to go through some of these, some different groups, some activating and some deactivating. Some of them are going to be, they're going to have some different levels of activation or deactivation. We'll have some of them that are strongly activating or weakly activating, those type of things, and that's what we're going to be looking at here. Let's first look at, we'll start with the activating groups. Let's look at strongly activating groups.